will be followed by other meetings in these cities. So the first speaker is Paolo Gibilisco from the University of Rome, Tor Vergata, and the title of the talk is A Gentle Introduction to Information Geometry. So it is 50 minutes talk, and then there will be room for questions. Thank you, Paolo. Please start.
Yes, so let me thank the organizer, Francesco, Rita, Patrizia, all the others that, for this opportunity, and let's hope to meet in present very soon. I'm going to review some of the basic resultant information geometry and to shortly address to some recent results that showed really, according to me, that the field is quite alive and there is a lot to do. So ambitious researcher, young researcher could think of working information geometry. I'm very happy because after me is going to talk Luigi Malagò. First of all, because it's a friend that I didn't see for a lot of time, and especially because he certainly is going to talk about application of information geometry. So I'm free to say that I don't care absolutely about application of information geometry. And this is not because I'm crazy, I'm mad, but because I'm a mathematician. So, you know, usually when we have to ask for money, we say, oh, our this field, first of all, is made by true theorems, and secondly, is very usable. And actually, it is true in general. But let me say, when we mathematicians meet and we talk about something, we never say it's true or it's usable, but we say it's beautiful. And information geometry is beautiful, and I'll try simply to convey some of this beauty, So first of all, I should move to the next slide. And let me remember this quote by a little masterpiece that is A Mathematician Lament by Paul Lockhart, where this teacher and mathematician explain how we should teach mathematics. We should teach mathematics as art. And I have the experience, also if I teach to a student in economics, that when you switch to this attitude and you say, well, we are just doing some fine arts, that is whose name is mathematics, the results for the students are really impressive. So is information geometry beautiful? Yes, and I would say especially because of the work of Danish Pets. There are many contributions that are basic to information geometry, but what's really the diamond in information geometry is the Pets classification theorem that I'm going to explain in a while. And Pets classification theorem is the cornerstone of quantum information geometry. And why is beautiful? For many reasons, but the main reason is that, say, in the classical setting, in the classical mathematics, now we can talk about the quantum mathematics. It is a mathematics of matrices indeed. There is also some quantum stuff really there. Well, in the classical setting, we have Fisher information, something from statistics. We have the theory of means, something very old in mathematics. And we have the theory of monotone function. These seems three totally different subjects. In Pets theorem, we will see that there's three totally different classical subjects. In the quantum case, have a very deep relationship and a beautiful one. So really, this theorem alone justify if you spend some time in studying information geometry and of course in doing some research. So we had, according to me, three real breakthrough in information geometry. First of all, by Rao, he's the person which identified the Fisher information as a Riemannian matrix on a statistical model. This is in the same paper where Rao proved the Kramer-Rao inequality. It's actually the Rao inequality. It is not due really to Kramer. Later, Chentsov had also this beautiful idea of characterizing Fisher information. So Rao said Fisher information is a Riemannian metric. And Chentsov realized that if you just ask that, if you want to use a Riemannian metric to distinguish densities, density vector actually, because it's for density vector here. And so what it is natural to ask that when you add some noise, so some stochastic transformation, it is more difficult to distinguish probability densities using this Riemannian metric. Well, if you add this, there is up to scalars only a Riemannian metric which this property that is exactly Fisher information. So Chentsov realized that Fisher information is not a Riemannian metric among many, but is very special on statistical models, namely on family of densities of density vector. And Petz exactly repeat the Chentsov argument in the quantum case. He doesn't find a unique Riemannian metric, but he classifies which Riemannian metrics on the quantum state space has this property of contracting under noise, contracting under stochastic transformation that in the quantum case is what is called a completely positive map or quantum channels. There are a manifold of names for the same object. So these are really the cornerstone, especially the Petz theorem. Let's see this in more detail. Let me say, if there are some questions that you want to ask now, please do interrupt me when you want. It is better. I think that if we have a dialogue, it could be more useful. So what is Fisher information when we are talking about density on R? It is just, well, we have this logarithmic derivative of a density. We imagine we can differentiate density. This logarithmic derivative is the score, and Fisher information is exactly, can be seen as a variance of this score. So it's given by this formula. And why is important to study? Well, statistics appear everywhere. In the Kramer-Rao inequality, when you want to have a bound on the variance of an estimator. But for example, when you are working with the exponential models, one of the most important class, well, you can prove the asymptotic normality of the maximum likelihood estimator, and the variance, it is exactly 1 over the Fisher information. So Fisher information, let's say, appears natural in statistics. It is like entropy. I would say only better than entropy in some sense. Rao in 1945 say, imagine we are talking with a statistical model, so a bunch of densities, and it is not difficult to see that the derivative, so here we have some regularity assumption, of course, the derivative of the density can be seen on the element of the tangent space in a certain point rho. Point rho means density rho. And Rao say, well, the expression for the Fisher information can be seen as a Riemannian metric on this set. I would say, what is Fisher information? It is like the L2 scalar product, but you have to divide by rho. So this division by rho gives you the locality, how this scalar product depends on the point of the manifold. So this is the idea of Rao that stayed there for a while without not a lot of application. But it is Chentsov to really change the situation. He say, okay, let's remain on the simplex of probability vectors. We want strictly positive probability vectors. In the quantum case, we want faithful states because we want to divide by rho. The tangent space can be seen as the vectors whose the sum of the component is 0. And the Fisher information is given by this expression. So this is like the ordinary scalar products, but you have to divide by rho. One may prove that the geodesic distance for this Riemannian matrix is exactly the Bhattacharya distance, which is 2 times the arccosinus of the sum of the square root of the components of the two density vectors. In a while, we will see why we have this formula for the geodesic distance. Well, first, because we may look at Fisher information in many different ways. For example, if we consider the Kullback-Leibel relative entropy, given by the formula that we have here, and we calculate the Hessian of the Kullback-Leibel relative entropy in a point row, well, we get exactly the Fisher information. So we keep in mind this, thinking, for example, to a quantum version of Fisher information. In the quantum case, we have the Umegaki relative entropy that is exactly mimic the Kullback-Leibel relative entropy for matrices, say. And so one can, for example, use this to see if we have something similar to Fisher information. And there is another way to see Fisher information. Is doing the first one to realize this seems to be the Wind, the important statistician. And the fact is the following. If we map the density vector into the sphere of radius 2 with the map which brings each density vector in 2 square root of rho, where square root of rho is square root of the components. So if you want, we have a point in L1 that we push in L2, taking the square root. What's happened? We have a map from a manifold, the simplest probability vector, to the sphere, another manifold, and we may pull back everything. When we have a map from a manifold to another manifold, we may pull back the geometric structure that we have in the arrival manifold. We can pull back in the first manifold. If we do this for the ordinary geometry, that the sphere, the two-dimensional sphere embedded in the three-dimensional space, for example, okay, of course, here we have the n case. What's happened? If we pull back this geometry, we have exactly the Fisher information. And so this explains here with in a single step why the geodesic distance is given by that formula, because that is the geodesic distance on the sphere when you consider the square root of rho and the square root of sigma of the two density vector. Here we are. So there are other ways to look at Fisher information, for example, using the logarithmic derivative, the symmetric logarithmic derivative. So Fisher information is the Hessian of the relative entropy. The pullback of the square root map can be seen using the score, the symmetric logarithmic derivative. Very good. What's happened? That in the quantum case, many authors try to find an analog of Fisher information. But which property should we have to use? Well, if you use the relative entropy by Umegaki, the trace of rho times log rho minus log sigma, you get indeed a Riemannian metric. It's the Bogoliubov-Kubo-Mori metric. It's very used in quantum statistics and in a lot of other situations. I guess we will see something about this later today. Or you may also, in the quantum case, you may consider the square root map for a state, and you may pull back the geometry of the sphere of the quantum state space. What you get is the Wigner-Jenaz information, and this is surprisingly due to myself. It was nobody realized this before. This was quite useful. So the Wigner-Jenaz information that we use to present, and we will see after in another way, is indeed this pullback of the square root mapping. And if you use the symmetric logarithmic derivative, you find another metric, different one, the Bures-Ullmann metric, also called the SLD metrics. And unfortunately, I would say in the physics literature, the Bures-Ullmann is called frequently the quantum Fisher information in the quantum case. Of course, it makes sense because in some senses was the first to be realized as such, but can be very misleading. There is not a single quantum Fisher information in the quantum case. There are many. So the problem is this a zoo of examples of instances, or there is a unified approach? The answer is yes. As I told you, it's due to Danish Pets, and the idea, wonderful idea by Pets, was to use the mean. Pascal said that man in nature is nothing regard to infinity, and is everything regard to nothing. So we are the mean between nothing and everything. Well, mean are important, but how to present them? There are many ways. One of the most useful axiomatization is the one I'm going to propose in this slide. Very much used. So a mean is something which associates to two positive numbers and third positive numbers with some property. So the mean of x and x should be x. We want symmetry, the second property. We want monotonicity, and we want homogeneity, and we want continuity. There are indeed some approach where these requests are relaxed, and but for us it's useful to consider, say, a good-looking mean. So means that has this all these properties. Examples. So no, first of all, how to obtain means? Well, if we consider this class of function, which is normalized, so f of 1 is equal to 1, symmetric, t of ft minus 1 is equal f of t. Symmetric here, it is not clear why we use this term, but this is what guarantees symmetry in the associated scalar product. And we want monotonicity and continuity. Well, if we have the class of function with this property, there is a bijection between numerical means and this function given by this formula, where the mean is of x and y is just y times f evaluated in x times y minus 1. Okay, so some example, the arithmetic mean is associated to the function 1 plus x over 2. The geometric mean is associated to the square root of x. The harmonic one to 2x over x plus 1. Let me call this mean Wigner-Jenase, because in the quantum case that we are going to see in a while will be associated to the Wigner-Jenase instance of quantum Fisher information. So each function gives us a mean. Here we have other example where you read WYD. This is the Wigner-Jenase Dyson information, and the function you see give you the mean that you see on the right-hand side, and they are associated, we will see, to the Wigner-Jenase Dyson information that is also an example of a quantum Fisher information. Actually, it's a family, a one-parameter family of quantum Fisher information. We have the logarithmic mean associated to the function x minus 1 of the logarithm of x, and also very strange mean, as you may see, associated to very strange function that do not have a name, and probably they, well, till now they do not deserve a name. Well, we have a beautiful non-commutative quantum, if you want, counterpart of this theory that is due to Kubo and Dando in 1980. So consider among the central joint matrices the strictly positive definite matrices. And a mean on this set is exactly a function which is associated to two means, to strictly positive definite means, associated a third means. And we mimic all the property as much as we can. So the mean of A and A must be A. We want symmetry, monotonicity, continuity. And the homogeneity property is substituted by this transformer inequality that we see at number 5. And the names comes from the fact that one of the first appearances of this non-commutative means is in the theory of circuits. So it is exactly the transformer you are thinking about it. Kubo-Dando give this axiomatization. They say, let's call a matrix mean, an operator mean, something which satisfies this axiom.
Excuse me.
Please.
Paolo, what does CM stand for? CM, capital CM, what does it stand for?
M, sorry, it is not written very well.
Okay.
M is
okay, C times times F. Okay. Yeah. Okay.
CM.
Yes. Another question. Is there also a generalization of mean to multi arguments, not only 2, but 3 n?
That's a beautiful question. Yes, indeed. Yes, indeed. There are a lot of results. I would say the most many authors, including Dennis Petz, made some steps. And finally, Lawson and Lim in 2008, as far as I know, because it's a very active field, find the general solution how to go from, say, a mean of 2 arguments to a mean of 3 arguments and more. For example, well, the non-commutative setting is rather delicate there, but for the commutative setting, we have a beautiful part of general theory. So using the barycentric map, you can go from, say, an n mean, a mean of n argument to a mean of n plus 1 argument. And you keep all the good properties, so homogeneity, monotonicity. It's a beautiful. I'm working actually on something related to this. So yes, there is.
And also associativity. Is there also some associativity, a form of associativity in that case?
I don't know. I don't know. What I realized for my own interest, I didn't know much before, is that all that property that I want, because I'm working on something different, not on information geometry, but still related to means, goes in any for any number of arguments. But associativity, I have no idea.
Okay, thanks.
Maybe later, if you want, I give you the reference. I know it's fascinating subject because it's old as at least as the Greek mathematics itself. So the fact that it's still so live and active is wonderful, according to me, according to my test. So Kubo-Dando say, let's call an operator mean something with this property. And of course, when you decide an axiomatization, means that you already have a theorem that characterizes. How to understand the characterizing theorem? First of all, for functional matrices, well, using functional calculus, we may have a function for, we have the logarithm of the exponential of the matrix with due hypothesis. And also we may talk of monotonicity when we are talking about positive definite matrices. This is the definition given by Lohner. And the operator monotone function are very much related. Well, they are related with a number of subjects, but also with complex analysis. So if you have a map that maps the upper half plane into itself and it's analytic, this is a peak function. Now, the operator monotone function, which are real function of real variable, well, a function is an operator monotone function, even only if it's the restriction of a peak function. This was the important theorem by Lohner relating operator monotone function to complex analysis. And also in this case, we don't want to consider all the function, but we have these 2 property, normalization, symmetrization. And so let me call F op the family of normalized and symmetric function, which are not anymore only monotone, but operator monotone. So monotone on matrices, on positive matrices. for example, the function that give us the arithmetic, geometric, and harmonic mean are indeed not only monotone, but also operator monotone. This is very restrictive. An operator monotone function is operator convex, sorry, operator concave. So it's a very, I mean, it's a huge class of function but with so much structure inside. It's a very strong requirement to be operator monotone. And so, of course, Kubo-Ando had this beautiful theorem, and they say how to get an operator mean. If you consider an operator monotone function in F-op, so normalized and symmetric, with this formula, you get an operator mean, and vice versa. Each operator mean comes from as a representing function f, to which is associated by that formula. Well, it is this formula is a bit complicated, but not too much, in the sense that if you have the commutator, if two matrices commute, so the commutator of A and B is 0, the operator mean of A and B, according to f, the representing function, is exactly A times the function calculated in B times the inverse of A. So we have exactly the formula we have in the commutative case, as it should be. So the above formula is this formula in the general case, when we have to take into account the fact that A, B do not commute. So operator means operator monotone function, and so we have some example. The arithmetic mean has the same phase, and the harmonic mean exactly has the same phase, but the geometric mean, as you see, is the one between the two lines, is much more complicated in the metric case than the geometric mean for positive numbers. And we know that the geometric mean stays between the harmonic and the arithmetic. Kubo and Ando proved that this property is true for any operator means. So we have the biggest one, which is the arithmetic, the smallest one, which is the harmonic operator mean. Inside we have all this word of the operator mean. So let's to explain Petz's theorem. Oh, sorry, Rita. When I have to stop?
So you will have to stop at like 20-25 minutes, something like that. But then we have 10 minutes discussion. So
yes.
there is.
Let's say 25 past 3.
Yeah, something like that.
Okay. Yeah. I was thinking.
I can remind you when it is like 5 minutes to. How about that?
Thank you, because I want at least to highlight. But I think I'm going also too fast, maybe.
Yes.
But I'm happy to have a question that slow my talk. So please interrupt me if you need it. So let's see. First of all, my final goal is to arrive to Petz's theorem, but to explain Petz's theorem, of course, we cannot understand something quantum before the classical version. So Chensov theorem say the following. Imagine we are on the simplex of probability vectors that we introduced before. And imagine we want a Riemannian metric such that when we apply a coarse grading, this is a language introduced by Petzs, of course inspired by statistical mechanics, namely a stochastic map, namely a linear positive trace preserving map. This coarse grading is muddying the waters, is making noise. So we expect that a Riemannian metric that is, say, statistically relevant should contract, should shorten the distance once you apply this map T. And when you require this at an infinitesimal level, what you get is exactly the inequality that you see. So T is a function on the manifold. And so on the tangent, so T moved the densities rho. On the other hand, its differential should act on the tangent vector. But T is linear, so its differential is T itself. And so to ask that at an infinitesimal level distances contract is exactly to ask that the scalar product of Tx and Tx in the point T rho is less or equal to the scalar product of x and x in the point rho. So this is the property that we want. Under noise, this Riemannian metric shorten the distances. And Chancellor proved that up to scalar, you don't have many Riemannian metrics, but only the Fisher information has this property. Only the Fisher information has this property. So we see that this is a very special situation. Certainly, for statisticians, one may say, who cares about this? It's a geometrical feature, nice, it's a curiosity, something, I'm sorry, something that, but the situation is not so. This is not a kind of side feature of Fisher information. This is crucial. This is crucial because when you want to understand Fisher information in the quantum case, you have necessarily to go through geometry, to this geometrical aspect. And it was Chancellor itself with his wife, Morozova, to try to make the next step, the quantum one. So he said, okay, what is the quantum analog of all this? Let us consider among the self-adjoint matrices faithful states, so positive, strictly positive self-adjoint matrices whose trace is equal to 1. And let's define a quantum Fisher information. What is a quantum Fisher information? It will be a Riemannian metric on this manifold of faithful states. It's a real manifold. It's a real manifold. Such that when we apply a coarse graining to this machinery, distances shorten. Well, what is coarse graining here? Well, we have a linear, completely positive trace-preserving map. Of course, in this case, in the quantum case, positivity should be replaced by complete positivity. So this is what we should call the coarse graining, some noise there. Or now we have the name quantum channel because this is basically quantum information, and possibly other names too. Chancellor and Morozova say, if we have a Riemannian metric such that the scalar product of TA and TA in the point T rho is less or equal than the scalar product of A and A in rho, well, we call it this a quantum Fisher information. But Chancellor and Morozova was not able to identify not even one case. So they didn't find any quantum Fisher information. But fortunately, Dennis Petz, after some years, solved the problem completely with a beautifully simple idea. Well, the idea is that we are in the non-commutative setting. So you cannot auto multiply it by rho because you can put some rho on the right, some rho on the left in some sense when you multiply it by rho. And the idea of Petz was saying, well, let's do this in all the possible way using the cumulando operator model, operator means. Let's see what I mean. So let's L rho the left multiplication operator by rho and R rho the right multiplication operator by rho. These are super operator, but they are if rho is positive, they are positive. So it makes sense to make the mean, the operator mean, associated to any operator model function f. And so it makes sense to talk about the mean of L rho and the rho and the inverse of this, because we have two positive superoperator, the mean is a positive object, and so we have the inverse of this. Well, ladies and gentlemen, maybe I want to go back to, well, no, I don't need to go back. Let me remind you, I told very roughly, I say, what is the commutative Fisher information? You have the ordinary, what we call the L2 scalar product, but you have to divide by rho, this localized. And here we have something similar, where the ordinary scalar product, quotation mark, is the trace of A and B. Well, the conjugate of B, but we are considered here as the self-adjoint case. What's happened? You want to divide by rho. What does it mean here to divide by rho? Simply to multiply, to apply the inverse of the mean of the left and right multiplication operator. So it is like if you want to distribute in all the possible way rho on the right, on the left, using several strange functions. And in the end, you are simply multiplying by rho, here multiplying by rho inverse. So the formula is in some sense exactly the same, quotation mark. And Pets prove that, with this formula, you obtain quantum Fisher information, so metrics which shorten under constraints, shorten distances, and vice versa. If you have an operator monotone function, the associated mean, with this formula, you have, from the mean, we have the quantum Fisher information. And each quantum Fisher information is associated to a certain operator mean by cuboando, and therefore to some operator monotone function in the sense of Lohner. These are all bijection, yes. This is a vast family of Riemannian metrics on the quantum state space. There are people spending their mathematical or physical career on one of these metrics, because they are quite different objects with quite rich structure. So they are not the same, absolutely. They are quite different. Also, if we have some structural theorem, you really may spend your career studying one of these. There is a lot to do. For example, we have only two cases in which you have the closed form from the geodesic distance. One is the Bures-Ullmann or symmetric logarithmic derivative case, where you have this formula for the geodesic distance. And the other one is the Wigner-Yanase case. As I told you, I was fortunate enough to prove that the Wigner-Yanase case comes from the square root mapping. And because of this, a one-line proof gives you the geodesic distance, because you have simply to put back the distance that you have on the ordinary, say, non-commutative sphere. Here we are. So, why information geometry it is worth to study? Because it's true, it's usable in a lot of applications. For me, especially because of this bijection that are due to Pets, and of course in some sense also to cuboando and Lohner, that say when you have an operator monotone function, you have associated an operator mean. When you have associated an operator mean, you have a quantum Fisher information associated. And vice versa, Each quantum Fisher information arises from an operator monotone, an operator mean by cuboando, and each means comes from a function. So these three very different objects in principle are, say, the vertices of a triangle, where you have this very, very strong link. So this is the basis where information geometry stands. From this, you have many directions. Some of them I cannot even follow. And maybe Luigi Malago will explain something interesting about optimization. I will talk about two new directions, or not very new. The first one is that was very surprising to me. This information geometry shed new lights on LP geometry. So I was very, as a student, my imagination was a bit limited. So I was thinking that we knew everything about, say, the geometry of the unit sphere in the LP space. Ladies and gentlemen, it is not so. The situation is very much worth study and difficult to study. Let me explain why. First of all, a contribution by myself and Isola. In general, if you have a Banach space which is uniformly convex and the dual is uniformly convex, example, LP spaces both in the commutative or in the non-commutative case, well, using the duality map, you may study and make calculation in an easy way somehow, the geometry of the unit sphere. When you have the three-dimensional space and you have the sphere, the Levi-Civita connection on the sphere, which is, it is simply the geometry that you have on the sphere. Well, for a Banach space like the LP space with which uniformly convex and with the dual uniformly convex, so it's with a lot of good qualities. This Levi-Civita connection can be studied because the LP space is not, of course, an Hilbert space. So we are not in the realm of Hilbert-Riemannian geometry, where most of in some sense, you may reproduce all Riemannian geometry, almost all Riemannian geometry, also in the infinite dimensional case. In general, it's not so for a Banach manifold. When you have in this case, a lot can be done. Why we were interested in this is due to Giovanni Pistone, that maybe is listening to this seminar. Together, Amari and Chenso, what they did, they generalized the square root embedding, and they say, well, let's study a different embedding. We bring rho in P, rho to 1 over P. As strange as it is, was not clear before of my work with Pistone that this embedding was from, say, L1 to LP. Why this is certainly trivial. And what's happened that what we proved, if we put together my result with Pistone and Isola, what we have, that the alpha connection, which are, say, the pullback of this embedding, are nothing else than the pullback of that Levi-Civita geometry on the unit sphere of the LP space. So, what I mean, alpha geometries are one of the most studied objects in information geometry. To myself, they are just the geometry of the LP sphere in a disguised form. So this was for me a surprise. For example, here you have this beautiful formula where you decompose the LP connection on the sphere as a convex combination of two flat geometry, the exponential geometry and the mixture geometry, where the geodesic are just the mixture models and the exponential models. So what we did, it is just to work the alpha connection in infinite dimension, and this is my slogan. So the alpha connection of LP sphere geometry in a disguised form. Who cares? Okay, this can be a nice mathematical fact, but is this useful? And one of my biggest surprise is that it is quite useful. So let's forget where we are talking about. Let's go to the Arnold problem. It was Arnold to prove that the Euler equation of ideal hydrodynamics can be seen as if you go in the right space in the volume preserved diffeomorphism, it's a geodesic on a sphere in some sense. So the dynamics can be geometrically characterized in a very simple way. And there are other examples like the motion of a rigid body. But certainly the hydrodynamic case is very exciting for the importance and for the complication of the partial differential equation that are behind this. Of course, when you reduce a complicated partial differential equation to, say, a movement on a maximal circle on a sphere, something can be better understood. And so Arnold himself asked, well, find, was very generic, find all the mathematical equations, dynamical equations, mathematical physics can be realized as a flow in infinite dimensional ellipsoids. For example, there is this very nice partial differential equation. Certainly, I had no idea before of this existed, which is the alpha Proudman-Johnson equation, where you have this parameter alpha. Not a case is called alpha. So we may ask, does this fit in the Arnold scale? Can be seen as something on a sphere, on an ellipsoid, somewhere in a complicated space? Well, who cares about this equation? Well, we care because this one parameter of partial differential equation, well, let me make some names dropping here. For alpha equal 3, you have the original Proudman-Johnson equation that is related to the two-dimensional incompressible Navier-Stokes equation in fluid dynamics. For alpha equal to 0, you have the Hunter-Saxon equation, which appears for orientation of wave massive direct pneumatic liquid crystal. God forgive me if I'm an expert of this field, of course. Absolutely not. For alpha
Paolo, you have 5 more minutes,
yeah,
so I'm warning.
I want to finish. Thank you. This one parameter, as you see, there are a lot of important names, and I would say real physics there that justify the interest in understanding this one parameter family of partial differential equations. We have a real breakthrough by Lennels and Michalek. They found, studying the diffeomorphism group of the circle, and after the quotient of the diffeomorphism group over the rotation of the circle, which can be identified with density, and on density we have the alpha geometries. They say, ladies and gentlemen, the geodesic equation for the alpha convection is exactly the alpha Proudman-Johnson equation. So they relate information geometry with this family of dynamical evolutions, so important. And they did it in general on any compact Riemannian manifold. And they studied this alpha geometry using the divergence. This is another idea of information geometry. And so I suggested them, well, why don't we use the pullback approach? Why don't we look at the LP spaces? And ladies and gentlemen, it seems, let me say it seems, due to the work by Bauer, Liu, and Mauer, that this proposal is right. So it seems that we may look to this very complicated family of a partial differential equation as, say, a maximum circle on an LP sphere. This can be very useful to study integrability, complete integrability of the partial differential equation. Really is a change of, can be quite useful. Just 1 minute to say that another recent result is that in quantum information, there are some measures of quantum discord, like the local quantum uncertainty, the interferometric power, that have been very popular here, because they somehow measure the difficulty of studying a whole quantum system from the components. These two objects, they seem totally different. Together with Frank Hansen and Davide Girolami, we show that they are exactly part of a unique family. So like using, of course, the Petz theorem, we realize that they are, let's say, each irregular quantum feature information has associated one of these measure of quantum discord. So two apparently totally different objects is exactly like Petz did, are indeed in a family, and so you may look, say, from above these two objects. These are just two problems. There is a lot going on in information geometry. It's a very active field. It's a very at the corner, at the crossroad of so many things, from differential geometry, probability statistics, quantum physics, that really it's worth a study for a young researcher, also for an old researcher like me. Thank you very much.
Thank you very much, Paolo, for this very dense introduction.